Welcome back to my course Aspects of Biochemical Engineering. Now, I think this is the last part of reactor analysis. We discussed the theoretical portion of the how to analyze the reactor analysis. Then we last two lectures I discussed several numerical problems just to have very clear idea about the reactor analysis, and this is the last kind of last lecture, and here I shall concentrate on couple of problems and how we can have a better idea on this analysis of the reactor. So, you know that if you look at this again here, we will consider now in this lecture I am going to consider all the different type of reactor, batch reactor we will consider CSTR, we will consider plug flow reactor. We shall show you that in case of CSTR and plug flow reactor, if you increase the flow rate, how is going to affect in the system, how if you increase the initial concentration of substrate, how it influence on the process. Though this I shall try to discuss. The another thing another very interesting thing also I try to incorporate that if you club this CSTR with plug flow reactor, how you can do the analysis. So, I hope by this lecture you can have very little bit clear cut idea how we can do the reactor analysis. To start with this, let me start with the batch process first. Now, if you look at here that we are planning to operate a batch reactor to convert A to R, and this is a liquid reaction. The stoichiometry is A to R, and the rate of reaction is given in the table. How long must we react in each batch for the concentration to drop from Ca is 1.3 mole per liter to 0.3 mole per liter, and this is the data that is given. So, if you look this problem is apparently is similar type as I discussed in the last lecture class, and let us see how we analyze this problem. Now, what we are planning to do? We want to reduce the initial substrate concentration from 1.3 mole per liter to 0.3 mole per liter, and so this is the T batch that equation that we have already we know. So, so here what we have the data of Ca, and also we have the data of minus Ra. So, here we can also find out minus Ra, that different value we add different value, we can do that. Then you can plot that minus Ra versus Ca. Then if we have this plot, we can calculate this. What is how you can find out the time required for the batch process, you can easily calculate. Now, this is how we calculated the data. That's one Ra is 1 by Ra. This is the whole data that we can calculate, and then we put this is the figure. This is 1 minus Ra by Ca. This if you put now this is this pattern, if you can see it is a little bit different as compared to the previous pattern. Previous pattern more or less we have the correlation is like this, but here it is like this. So, you know that here what is happening, that here this is 1.3, this point is 1.3. So, 1.3 to 0.3, this is 0.3. Then what is the time is required? So, so if you calculate the area under this curve, then then what is coming? This will come around 12.7 minutes. And this will come around this area under this curve will come about 12 point. This is the 12.7 minutes. That is the time. You can if you calculate, you can find it out. So it is very easy to do that, because so only that you have to again I am telling you that you don't have to count the number of squares of the centimeter graph paper, because this is very laborious. That if you want to solve it, you have to do it try to do it very easily. You have to make a rectangle like this, that so you can consider this is a triangle, you can consider this is a rectangle, am I right? And this is again is a triangle, then it is a rectangle. Now again this you can more or less you can consider as a triangle, then you can consider this a rectangle. So approximate value, because graphical method exact value it is very difficult to find out, but you can find out the approximate value time required for the batch process. Now for the reaction of the first problem, what size of a plug flow reactor would be needed for 80% conversion of the phase stream of 100 moles of A at CA0 1.5. Now here I want to point out that in my last presentation I forgot to discuss a similar type of problem on plug flow reactor. I hope it is similar type of problem. So if you understand that this also this you can solve it that also you can understand very easily. Now here that what is they are saying, suppose this is the plug flow reactor, that they are saying that this is the input, this is the output. Now what is the input that we have here flow rate is equal to 1000 moles of A per hour, am I right? And what is CA0? CA0 equal to 1.5 mole per liter. So this is so what size? So 80% conversion. 80% conversion means how much substrate that remain? That 20%. So 1.5 into 20%, that is 0.2, that is equal to 0.3. Then here the Ca value will be what? 0.3 mole per liter. Am I right? So we shall have to find out what size of the plug flow reactor is required to reduce the substrate concentration 1.5 moles per liter to 0.3 moles per liter, and the flow rate is 100 moles of A per. Now here I want to again one thing I want to point out that F is given in moles per hour. Am I right? F is given in 100 mole per hour. Am I right? So if you want to convert it per volume, so what you can do? You can divide by 1.5 Ca0 the mole per liter. So mole will cancel. So you can find out liter per hour. This is you can easily find out the volumetric flow rate. You can calculate like this. Now this is as I pointed out that first you have to write what are the things given in the problem, that these are the things given. Ca0 is 1.5, you see that 1.5 is the Ca0, and Xa is the 80% conversion is the 0.8, and Fa0 this is 1000 moles of A per hour, this you can convert per unit. This is very important because because you know that this suppose here it is a minute is tau plug flow reactor you calculate in minutes. So this flow rate also should be in minutes, otherwise there will be some error in calculations. Now CAF equal to this is 0.3, this I have already shown you, I do not like to explain further. Now the equation is that equation for this is the tau plug flow reactor is this, the same as your batch reactor. The integration can be evaluated graphically under the curve Ca versus 1 by R, Ca0 to CAF. Now this is the curve that we have. This is 1.5. this is 1.5, this is 1.5 this point, and this is 0.3, this is 0.3 mole per liter. So, area under this curve I showed you how to calculate, and then you find out tau you can find out tau plug flow reactor. Once you know tau plug flow reactor, then tau plug flow reactor is what? Tau plug flow reactor is equal to what you can write equal to V by F. Am I right? What is the F? If I have already shown you F, so V equal to tau plug flow reactor into F. So, you can find out the volume of the reactor. Now, here in this problem it has been solved in the similar way, only they have shown that Fa0 is equal to what? CAF is 0 into F. Am I right? What is Fa0? Mole of A per unit time. Am I right? So, this is equal to what? Mole of A per unit volume. This is volume per unit time. So, this volume will cancel. So, mole of A versus per unit time. So, this is same. So, it is like this. So, if you divide by this, you will get the volume, that the same thing you will get. So, volume B by F equal to tau plug flow reactor. This is similarly we calculate here and find here that you can find that the volume of the reactor is coming, plug flow reactor is 190.97 liters. This is how we can calculate. This is here tau plug flow reactor has been calculated. This I forgot to mention. This is 17.18 minutes. So, you can easily do the calculations here. Now, next problem, next couple of problems are very interesting. That if you look at for the reaction in the first problem, what size of, previously we also discussed about the plug flow reactor. Now, we are talking about the CSTR. What size of CSTR is needed for 75% conversion of feed stream containing 100 moles of A per hour, Ca is 1.5. So, it is basically like this. This is a continuous process. We have continuous start tank reactor like this. So, here what is happening? This is here it is to 1.2 mole per liter. So, 75% conversion, then how much remaining? 1/4. 1.2 into 1/4 is coming around 0.3. So, here is the 0.3 mole per liter. Am I right? So, so in this reaction for 75% conversion, and what is the Fa? Fa value, Fa0 value is equal to 1000 mole A per hour. This is given here. So, you have to find out what volume of the CSTR is required. Now, repeat the first part. The modification is the feed is double. As I mentioned, the feed rate is double, because initially it was how much? 1000 moles of A per hour. Now, if we make it 2000 moles of A per hour, then what will be what will happen? That we shall have to find out. Now, next problem, that CA0 value was 1.2. Now, if you increase to 2.4, but flow rate the Fa0 is same, then what will happen to this particular size of the reactor? So, the different way we want to solve the problem and try to find out how it affects the process. Now, in this problem that CA0 is value is given, Fa is given, we only convert in per minute, because it is given per hour, and conversion is 0.5. The CAF I have already shown, it is 0.3, and CA now CAF, and so RA we can minus RA we can 0.5. How we can find out? Tau CSTR equal to CA0 minus CA minus RA. Now, in this problem, because if you this is the repetition of the previous problem, we have the figures, the CA versus minus RA. So, since our substrate concentration is 0.3, so we know at 0.3 what is the rate of reaction. This is about 0.5. From the table we can find out this is about 0.5. Now, as I mentioned, tau CSTR is equal to CA0 minus CA minus RA. Am I right? So, this is equal to, also we can consider CA into XA minus RA. Why? Because XA equal to CA0 minus CA by CA0. So, I can find this is equal to, see, they multiply by this. So, this is how it has come. So, we can put this equation 1.2, 0.75, 0.5, then we can easily find out the volume of the reaction. Once we know the volume, then we know the I have already shown you how to calculate the volumetric the flow rate. Then you can find out the volume of the reactor is 25 liters. Though this you can solve graphically also, that you have already drawn this plot. So, this is 1.2 in the graph, this is 1.2 is there, and this is 0.3 is there, and this is simple rectangle. Am I right? A length into breadth. If you multiply it, you will get. You don't have to do this numerical analysis. Simple. But through graphical method also you can find out the time required for this. Once you require time, then you put this value here, time value here, and this equation you can put it, that this value, put this in the equation, you will find 25. So, this time, this equation here, you use this equation, but with in place of using this equation through graphical method also you can find it out. Now it is seen that that a volume of the reactor is proportional to Fa0. Now, therefore, double the feed rate, the volume of the this 50. This is 25 liter into 50 liters. So, how you can justify that? How you can justify that? This is volume of the reactor. Volume of the reactor, you can see this is in this problem. This here you find out the volume of the reactor is proportional to this. If you keep other constant, then if you make it double, then naturally the volume will be double. That is, since is proportional to this is double, then this volume will be, if feed rate is double, then volume also will be double. That is what we expect. Now, next problem that we have, if the concentration is double, the initial concentration is previously it was 1.2, but now we are increased to 2.4, other remain constant. This is 0.3 and other things. Then you put this, then conversion efficiency also changes, and then we put this equation, then we find out this the time required in CSTR is 4.2 minutes. But we can solve this then graphically also. If you know this is 2.4 and this is 0.3, so the area of the rectangle you can find out, and that is also will come at 4.2 minutes. Now, once we find out this time, we can easily calculate the volume of the reactor, because this we can easily calculate, because the volume of the reactor is equal to tau CSTR Fa0 into Ca. So, I hope I can explain that, because the tau CSTR is equal to, as I mentioned, C A 0 minus C A minus R A. Am I right? So, here is this is equal to X A into C A 0. So, what is the F A 0? F A 0 equal to C A 0 into F. And what is tau CSTR? Tau CSTR equal to V by F. Am I right? So, what I can write that that here what we can write, the volume of CSTR is equal to what? And the F into tau CSTR. Am I right? Now, what is F? F equal to F A 0 by C A 0. So, I can write this is F A 0 by C A 0 into tau CSTR. So, this is how it has come, this is how we have written here, and we put the value here, we can get the volume of the reactor. So, we can easily calculate the volume of the reactor here. Now, last problem that I am going to discuss, this is also very interesting. Now, before I go to the problem, let me discuss something that I tried to explain before also, that suppose we have a plot minus R A versus C A, am I right? And we have plot like this. Now, suppose I want to this is the same reaction A to B, and here this is C A 0, and we can this is, let us assume C A, this is C A dash, am I right? Now, so you have two pattern, what I wanted, this I discussed before also, we have two different patterns. Now, if you have these patterns in this particular reaction, then same type of reactor may not be suitable for the system, because one reactor may be suitable for conversion of C A 0 to C A dash, and another type of reactor may be suitable for conversion of C A dash to C A. So, if you consider the C A 0 to C A, and our what is our target? Our target is, if you look at tau CSTR is equal to V by F, am I right? And tau plug flow reactor, that also equal to V by F. So, we shall have to find out under what circumstances this is minimum. This is minimum, that is only our selection. Now, when C A 0 convert to C A, the area under this curve, this is equal to tau CSTR, am I right? Tau CSTR. But area under this curve is tau plug flow reactor. So, obviously, tau CSTR here is much less as compared to tau plug flow reactor. So, what is our selection for this time of reaction? Our selection goes to tau CSTR. But here it is something reverse. Here you see the when C A dash to C A, then area under this curve will be tau plug flow reactor. But when you go for plug CSTR, this is tau CSTR. So, naturally this is much less as compared to tau CSTR. So, our choice is tau plug flow reactor, if you conversion of C A to C A dash to C A. So, our choice, so if you look at reactor, that our strategy should be like this, that initially this should be CSTR and followed by plug flow reactor. So, this is CSTR, this is plug flow reactor, this is C A 0 to C A dash, and this is C A. Now, why I told all these things, because now coming problem that we are also going to deal with similar type of things. Only the thing is that how we can find out that if you operate the CSTR, how we can find out how much where substrate is converted. and if you followed by say plug flow reactor, how much substrate will be converted. So, what is the value of Ca dash and what is the value of Ca that we are going to convert. Okay. So, this is like this, that in the liquid phase reaction A to B plus C is conducted isothermally. Isothermally means temperature remaining constant at 50 degree centigrade at continuous start tank reactor. The inlet concentration is 8 moles per liter at space time 5 minutes. Space time means tau CSTR. Am I right? Tau CSTR is 5 minutes. The concentration of the the exit stream is 4. The kinetics is given here. So, calculate the K constant. We can do it very easily, because tau CSTR is equal to what? That I can write Ca 0 minus Ca minus Ra. Am I right? What is Ca 0 value? 0.8. 0.8. This is what is Ca? 0.4. And what is tau? This is tau CSTR value 5 minutes. So, you can easily calculate the value of Ra. So, that is exactly, once you know the Ra value, then we know the Ca value, that is 4 under steady state conditions. So, we can easily calculate the value of K. So, it is done, it can be done very easily, that rate constant we can calculate very easily. Now, next part is that if a plug flow reactor of the same volume is added in series after the existing CSTR, what will be the concentration of A at the exit of the plug flow reactor? So, here I want to state only one thing, that since it is connected with the same volume, same flow rate, I can assume the tau CSTR is equal to tau plug flow reactor. So, only we shall have to find out at that particular situation what will be the concentration of the substrate at the exit stream from the plug flow reactor. This is the problem. Now, this is what is given in the problem. Ca 0 equal to 8 moles per liter and Ca is 4 mole per year, Ca 0 is 5 minutes. So, this is the equation that we have. Now, so if you put this equation, you can easily find out. You can easily find out the value of K. Value of K is if you assume this is first order reaction, so it is minute inverse. The unit will be minutes inverse. Now, in the second part of the problem, that here we have 8 mole per liter. Am I right? 8 mole is converted to 4 moles. Now, when same volume, we use a plug flow reactor we use here, and what will be the Ca1 value, that we shall have to calculate. And what is our equation that we have? Tau plug flow reactor equal to d minus dCA by K into Ca. So, we can easily solve that this is equal to like this, ln Ca by Ca1. So, this is that as the same volume is used to, I can assume the tau plug flow reactor equal to tau CSTR. Now, we can write 5 equal to 1 by K. Now, if you look at this equation, that ln Ca, what is Ca is 4 and Ca 1 here we shall have to calculate. K value also we have already determined. So, if we put all the values here, then we can calculate the Ca value, and which is coming around 1.47 mole per liter. So, therefore, the concentration at the exit stream of plug flow reactor is 1.47 mole per liter. So, in this in this lecture I try to point out that by using the batch process, using if you run a particular batch process and try to find out the rate constant as the different substrate concentration, how we can find the batch time that you can calculate, and from this same data we can also calculate that what is the time required for the 80% conversion, 75% conversion or 95% conversion in the plug flow reactor. Same type of thing we can do in case of CSTR, but at the same time if we wanted to increase the flow rate, what will be the effect on the process, or if we increase the substrate concentration of this initial substrate concentration in the continuous process, that how is going to affect the process. So, this I showed in this problem, and finally I discussed when CSTR club with plug flow reactor, how you can analyze the process, and we can calculate the substrate concentration in the existing both in the CSTR and the plug flow reactor very easily, provided we have all the information that is available in this problem, that we can determine the different parameters and put these values, and then we can find out the concentration of the substrate at the existing. So, I hope this you will be having very clear idea for the reactor analysis, and I request all of you, please put your pen to it. You try to solve is individual problem by yourself, so that we can have a clear idea on this process. Thank you very much.